I'm Raja Sivaramakrishnan. I'm a software engineer at Volterra. We're a startup based out of the San Francisco Bay Area. And today, I will be talking about the work that we have done to integrate Envoy with DPDK and virtual networking. Quick overview about our company. We are an edge services company. We believe that with the advent of many smart connected devices and the explosion of bandwidth that's going to happen with 5G, increasingly, a lot of the traffic on the internet is going to be generated at the edge and pushed upstream, as opposed to the early days of the internet when most of the content was downloaded by users from upstream. So that is the problem we're trying to solve. And towards that end, we're building our own infrastructure. So we have our own private backbone. And we have several edge sites on this backbone. And at each of these edge sites, we expect to have multiple tenants connecting to the Volterra infrastructure. And these tenants would generate a lot of traffic towards the edge site. And we would like to selectively process some of that traffic at the edge itself. And in some cases, we want to load balance that out to servers running elsewhere. And that could be either in the public cloud or in a private cloud of an enterprise. Envoy is a big part of the stack that we run on the edge site. And we've made some extensions to Envoy to support that. So for cases where we want to handle the traffic locally on the edge site itself, we've added support in Envoy to use JavaScript as a language for filters in addition to Lua. And we believe that JavaScript is much more widely used than Lua, so it might be preferable to write those filters in JavaScript. We've also added support for multiple virtual networks, making Envoy multi-tenant. And we do that with virtual networking, which I'll talk about in later slides. And finally, in this scenario, we expect that performance would be critical. And that is where DPDK comes in. We expect a ton of traffic from devices to the edge sites. And key metrics would be the number of packets that you process at the edge site per second and the latency of those requests. Another thing I want to mention is that in our deployment, Envoy does not run as a sidecar. It runs as its own process inside a container. It gets packets from the wire. And if it chooses to load balance them, it would send them back out on the wire. And there are cases where it would process them locally. So today, Envoy uses the kernel network stack. And there are some performance issues with using the kernel for networking. So we have to make system calls from an application. And these system calls typically are quite expensive. In addition to that, whenever we transmit or receive packets, there are interrupts. And that, again, is a drag on performance. We have to copy data between user space applications and the kernel. And that again hits performance. And there are also context switches, especially when you're blocking on I/O and you need to be switched back in. There are overheads associated with that, too. So the net result of all of this is that with a kernel-based application, we can process a few 100,000 packets per second. And not all of that can be attributed to the overhead of the TCP stack itself. There's all this additional infrastructure that's around the network stack, system calls, interrupts, context switches, and all of that. That is what contributes to the bulk of the overhead. There have been papers which have showed that the overhead of TCP itself is not as much compared to these other additional overheads that we have. So that is where DPDK comes in. So DPDK stands for Data Plane Development Kit. It's a set of libraries that was originally developed at Intel, and it has since been open sourced. And there's a pretty healthy community of developers working on DPDK. And the design goal of DPDK is to solve some of these performance overheads associated with the kernel network stack. So DPDK does all of the I/O in user space, so we completely bypass the kernel. And it continuously polls for packets, so that way we don't have the overhead associated with interrupts. It also uses huge pages. So instead of the typical 4K page size, you can use either 2 megabytes or 1 gigabyte huge pages. And that helps with performance by reducing the number of TLB misses. And the DPDK libraries have APIs that allow for easy communication between multiple CPU cores without using locks, and APIs to do batch processing of packets. So for example, if you're sending a lot of packets out, instead of touching the NIC for every single packet, you can send a burst of packets and touch the NIC just once, and that, again, helps significantly with performance. So the net result of all of this is that with DPDK, we can achieve an order of magnitude better performance than you can with the kernel network stack. The amount of processing that you can do determines how many packets you can process per second. So if you have an application that does a lot of per packet processing, of course, the numbers would be a little smaller. But for simple benchmarks, DPDK has been shown to have an order of magnitude better performance than the kernel network stack. So on top of DPDK, we've added support for virtual networking. And this is what allows support for multi-tenancy. So each tenant would get its own virtual network, which is basically its own VRF. And on the wire, we use overlay tunnels. And the overlay tunnels are what separate the virtual infrastructure from the physical infrastructure. So you could have changes in the virtual network without having any impact on the physical network infrastructure itself. And for that, we've built a vRouter module and integrated that with DPDK. So it is this module that handles packets coming in from the wire and also in the other direction. And applications can run on top of the vRouter, either in a container or a VM. And performance is best when the application also uses DPDK. So if the vRouter uses DPDK and the application doesn't, it doesn't improve performance significantly. And for that reason, we've extended Envoy to also use DPDK, because Envoy is an application that runs on top of our vRouter. So now that we moved all of the packet forwarding into user space, we need something that should replace the kernel network stack. And we are using an open source project called FStack. FStack is based on the FreeBSD networking stack, which has been around for a long time and has a pretty good reputation. And what FStack did is to take that FreeBSD network stack and integrate it with DPDK. And we have linked Envoy with FStack. And we've also made some changes in libevent. Previously, libevent used to sleep in an ePoll. And with our changes, libevent doesn't sleep. It continuously polls for packets. And we also have shared memory between Envoy, the process running Envoy, libevent, and FStack. It's all in one process. We have shared memory between that and vRouter. And we use the user space vhost mechanism for that. So the vhost mechanism was initially added inside QEMU as an optimization for handling traffic from VMs. Initially, the vhost backend was inside the kernel. And a couple of years back, that infrastructure was extended to move it into user space so that it could run in virtual router or virtual switch environments. And that is what we use to communicate between Envoy and the vRouter. So the user space vhost sets up the shared memory, and then any packets exchanged between Envoy and the vRouter are sent over this shared memory. So I mentioned that we have one process which runs Envoy, DPDK, and FStack. We could extend that to have multiple instances of the same process, and the vRouter could load balance the traffic across those multiple instances. So this picture shows the forwarding path. So we have packets coming in on the wire. So you have the orange, which is packets on one virtual network. So because we use overlay tunnels, there is an identifier inside the packet that identifies which virtual network the packet belongs to. And we have the vRouter process, which itself uses DPDK, so it's continuously polling for packets. So the vRouter process polls for packets, then does whatever is necessary to handle the virtual networking part. So typically that would include decapsulating the packets and figuring out which virtual network that packet belongs to. And in the opposite direction, the vRouter would encapsulate packets into a tunnel and send them out on the wire. So once the packet is decapsulated and vRouter has figured out which Envoy instance the packet needs to be sent to, it puts the descriptor to the packet in shared memory. And we have this other process, which is Envoy linked with DPDK and FStack. That process is continuously polling the shared memory for packets. So the packet enters initially through DPDK and then into FStack. And as I mentioned, libEvent is now continuously polling for packets. So it pulls the packet up from DPDK and dumps it into the socket. So we've added the ability to tie a socket to a particular VRF. So if you have multiple virtual networks, you can have socket 1 belonging to one virtual network and socket 2 belonging to a different virtual network. So once the packet is in the socket, then Envoy invokes FStack calls instead of the traditional socket calls. And then it does whatever processing needs to be done. If the packet needs to be sent back out, it would be deposited into socket 2, which could be in a different virtual network. And then that packet is sent out, again, using FStack and DPDK into shared memory. And then vRouter would take care of encapsulating the packet and sending it out on the wire. So this is a quick summary of the changes that we had to make in Envoy to get this working. So we added Bazel external repositories to include DPDK, FStack, and libEvent. libEvent polls continuously, as I mentioned. And libEvent calls into FStack to accept new connections or to listen for connections. Inside FStack, we added some support to support AF packet interfaces and VirtIO. And we also added support for IPv6 in FStack because that was not supported. And we added support for multiple VRFs in Envoy. And that's the API to tie a socket to a particular virtual network. And inside the Envoy dispatcher, again, instead of sleeping, we continuously poll. And we can do that on a per socket basis. So there could be the main thread of Envoy, for example, could still be sleeping on inside libEvent, but the worker thread could be continuously polling on sockets. And finally, we had to move some of the code from the main thread of Envoy into the worker thread, because FStack expects that any sockets that are created in the context of the same thread. So we couldn't have sockets that were created in the main thread and then handed off to the worker thread. So we had to move a bunch of that code from the main thread of Envoy into the worker thread. We have some initial performance numbers. This is work in progress, so please treat it as work in progress. These numbers are on VMs running in Azure Cloud. So we have a client connecting to an HTTP server, and in the first scenario, it's going through Envoy 1.8 unmodified. And in the second scenario, we have Envoy with FStack and DPDK. And in terms of requests per second, with the unmodified Envoy, we got about 172 with a latency of about 4 milliseconds. And with the Envoy with FStack and DPDK, that number was close to 500. And the latency was a little over 2 milliseconds. We're now in the process of measuring these same numbers with bare metal, because on Azure, we see some variance in the numbers, so it's hard to reproduce these numbers. So what I'm presenting here are the best case numbers, and we don't get the same numbers on every run with Azure. So we're trying to do this with bare metal. I think that's the right way to do the performance benchmarking. And once we have some numbers to share, we'll publish those. So in summary, our main contributions, we believe, are addition of multi-tenancy into Envoy, and improved performance with integration with DPDK and FStack. We plan to publish a blog in the future once we have numbers with bare metal and more test scenarios. And our website is best.io. Yeah, our blog will be published off of that. And we believe that this work could also have other applications. So for example, inside the Istio community, there's talk about using Istio CNI and sidecar-less Istio. And we believe some of this work could be applicable in those scenarios too. So that's all I had. Thank you. Any questions? Yeah.
Can you kind of characterize the overhead that the kernel networking has compared to all the things that are already going on in user space and Envoy, like the Volterra and JavaScript plugins and so on?
Yeah, so the question is, can we characterize the performance overhead of the kernel network stack as compared to the filters that execute within Envoy with Lua or JavaScript? So for the performance test that we ran, we did not have any Lua or JavaScript. So I don't really have numbers there. And hard to say how that compares with the overhead of the kernel stack itself.
I mean, even just the raw, pure processing of Envoy.
Yeah. So I don't think all of the overhead that we see with the kernel stack can be attributed to Envoy. In fact, I think that it's not even a majority of the overhead, because as we saw in the numbers, the latency went down from 4 milliseconds to 2 milliseconds, but we're still running the same Envoy code, but just not using the kernel network stack. So there is some overhead for sure, because for the same scenario, we also tested client going directly to the server, and the number was about 520 requests per second, and the latency was 1 millisecond. And when we used Envoy with FStack and DPDK, the request per second was about 500, and the latency was about 2 milliseconds. So we added about a millisecond of latency. How much of that is just due to Envoy, I'm not exactly sure, but I would guess more than half of that is the overhead of going through Envoy instead of going directly from client to server. Yeah, go ahead.
Two-part question. The first is, in terms of the promise originally of DPDK, it's really promises orders of magnitude improvements in performance. Do you think we're going to see that actually manifest itself, and all the, similar to Josh's question, all the extra overheads are going to help reach out some processing? Second question is about the fidelity of using like the TCP stacks. Often folks are generally concerned about, just in terms of, will they support the full set of features that are actually required for all the range of clients and flow control schemes, what it needs, and these kinds of things.
Yeah, so there were two questions there. The first one was, does DPDK really deliver on the promise of order of magnitude improvement in performance when combined with everything that's going on within Envoy, with potentially with other filters and things like that? So you'll see a lot of benchmarks with DPDK which show fantastic numbers. And usually those are for cases where there's very little packet processing that's happening. So you get a packet, you do a MAC lookup, and forward. And for that kind of benchmark, you'll see line rate with 10 gig NICs on a single core. But what we've seen in practice is that that's really not practical. In most cases, there's enough that needs to be done with every packet that achieving 14 million packets per second is close to impossible. So, for example, we run vRouter with DPDK. And the amount of work that we do in vRouter itself brings the number significantly down from, say, 14 million packets per second to a handful of million packets per second. So as you add more processing, it's expected that that number will continue to go down, but we still believe that it's going to be significantly better than what you can get with the kernel network stack. And sorry, what was the second question again?
It was about just the fidelity of the TCP.
Yeah, so the second question was, how good is the TCP stack? So we looked at what options we had, and the reason we picked FStack is it's based on the FreeBSD networking stack, which has been around for a long time, and it has a pretty good reputation. So whether it supports everything that's there in the Linux kernel stack, I'm not sure, but I think of the options that we have, I think FreeBSD is a pretty good choice.
At one point you mentioned that same level of performance. Why is that?
Yeah, so question is, if the application does not use DPDK, but vRouter itself uses DPDK, the performance is not as good, and why is that? And the reason for that is the application would incur the same overheads that are associated with the kernel network stack.
Because it's also going through the kernel.
Yeah, so you would have to make system calls to send a packet to the application, which hurts vRouter, it also hurts the application. Okay, thank you.